Okay, so let's look at the second half of 3-3, which is over logs. And we're going to start off with doing some additional problems, just to see if you have a handle on what we were doing yesterday. So take out your extra sheet of paper. We're going to use some of the properties. This would be the time to ask questions if you were uncomfortable when you started your homework. So these are additional. Example 1 problems. So problem A. The natural log of the 4th root of E. There are two ways that we could approach this. And I'll talk about that. But what's the first thing we should do? I have a log, no equal sign. What's the first thing?
Put it in that form.
Well, first, you're right, but first I want to do equals x. Then, that form, what's that form that I want to put in it? What's it called?
Additional.
Exponential. Oh, so we want to put an exponential form. Do I see a base? No. It's e, because it's natural log. Whenever it's ln, the basis is e. Before I put it into the exponential form, though, I like to take care of this right here. So let's convert that to a base raised to an exponent. So e underneath here is raised to the first power, right? So how does that convert base e to its exponential form? E to the 1 goes in the numerator, the root goes in the denominator. So e to the 1/4 equals x. Now we can put this into exponential form, right? Or can't we use our properties? What is the answer for x when the base of the log and the base of what we're taking the log of are the same? What's the answer? Not 1. It's whatever that exponent is. Whatever the exponent is, that's what x is going to end up equaling. So x is equal to 1/4. Now you could have instead, bless you, put it into the exponential form. We didn't change it and put it into exponential form, but you could have. Well, maybe I'll do it. So if I put it into exponential form, the e would have gone here, and then the e to the 1/4 and the x would switch places. So I'd have e to the x is equal to e to the 1/4. Then wouldn't x equal 1/4? Either way, so this is an or. Either way, you can look at it. Doesn't matter. Yeah.
When you switch it into exponential form, you get rid of that.
Yes.
So it doesn't get long.
Correct. Are we good with that? All right, so let's look at B. You good? Okay. So let's look at B. We've got log base 3. So when you're doing your bases, make sure you really drop them down. If I can't tell the difference between your base and the number you're taking the log of, you're going to get marked wrong. So just be careful. So again, there are two ways to approach this one. Here's way 1. Set it equal to x, and then put it into exponential form. So what's its exponential form? What's the base? So 3 to the x is equal to, and switch the 81 to the x. Well, I already did that. Equal to 81. 3 is the smaller of the two numbers. Can I convert 81 into 3 to something? Yep, so I've got 3 to the x equals, there are 4 3's in 81, so 3 to the 4. So what do you conclude? X equals 4. Now, I could have instead, or, what could I have done with this? See how the base of 3? I could try to apply my properties. Can I change 81 into a base of 3 so that the base here and this base would be the same? Sure, so I could make it log base 3 of 3 to the 4th, right? And so because these are the same, equals x. Doesn't x equals 4 also. We have the same answer. Just two different ways of approaching it. Using your properties or putting it into exponential form. You choose whatever way you're most comfortable with. It doesn't matter. Okay? Alright, so look at C. This time we have log base 5 of the cube roots of 25. So I'm going to have you do that one on your own. You decide how you want to do it. You could do it using properties, or you could do it using exponential form. My suggestion would be that you take care of, convert this 3 over this, or the cube root of 25, convert that first. You definitely want to change 25 into a base with a power though. Just saying. If you've got a number underneath a radical and it's not a prime number, I would change it into its primes. So when you get an answer, I want you to share that with those around you. All right, so chat with somebody around you, see if they agree with you.
I didn't do it, but that sounds right. I looked down government and
Let's see what you get.
How do you do it? You don't know.
You said that a little too loud. You couldn't see.
I didn't do it.
Quincy darling, are you here to observe or are you here to work?
I'm here to work. Are you here to
Look
work?
at-
So Quincy, tell me what I'm going to do. Oh my God. What are we going to do, Quince? Log base 5. What does 25 convert into? How can you convert 25? Can you convert 25 into a base of 5?
Yeah, I was just gonna say
How many 5s are in 25?
that.
2. So you get the cube roots of 5 squared, right? Then how do you convert this cube root into a base of 5 with an exponent?
Put the 2 over 3.
Very good. So I've got 5 to the 2/3. Then what happens when these are the same?
Cancel. X equals 2.
X equals 2/3. See, you can do it. All right, so because Quincy was not participating, we'll do another one.
Oh, one small.
Go past that.
So there's that one. You could have, well, you could have done it in exponential form, right? You would have taken 5 to the x is equal to 5 to the 2/3. And so then you would conclude that x equals 2/3. Question. So you try this one just to double check, make sure everybody understands what's going on. Log base 3 of the 7th root of 27. Log base 3 of the 7th root of 27. Don't let a 7th root bother you, it doesn't matter. So see if you can convert 27 to a base of 3, because that's the base of your log. Try to use those properties. Much easier that way. When you get an answer, compare your answer with those around you. Quincy and Ellie, discuss. Quincy and Ellie. Describe.
Allie and Ellie. Oh.
Girl, right in front of you.
It's like, did I say the wrong name? It's looking at me like I'm shaking.
Oh, yeah, 3 over 7. It is 3, yeah.
So what's the answer that we got?
3 over 7.
Everybody agree? 3 over 7? That's not so bad. Not so bad, right? Nope. 27 can be converted into a base of 3, so that's 3 cubed, right? Then whatever that's raised to, in this case 3, it goes in the numerator of the fractional exponent, and the root that we're taking goes in the denominator. And then because the base of the log and the base of that power are the same, the exponent is our answer. Now again, you could have done it in exponential form, taken the 3 here and raised it to the x, and put the 3 to the 3 sevenths over to the right, and then your exponents would have been set equal to each other. So we're good with that. Now let's look at something that we really did discuss, and let's see if we can figure out what to do. Now we have an equation. Log of x is equal to 2. You can do this without a calculator. What do we do first? I actually have an equal sign this time. I don't have to add an equals x, but my x is within the log. So I have one log in an equation. We need to recognize our base. What's the base of the log? 10. Now when I recognize the base, Logan, what do I do? Yep, so I take my base of 10, right? Put it into exponential form, and then I switch these two. So 10 squared is equal to x. Piece of cake, right? What's 10 squared?
Wait, why is
So I took my base.
So where did we get the 10?
Because if it's not there, it's understood. Remember, that's our common base. So if they don't write the base, it's understood that it's 10. So we want to always write in that base so that we see it, so that we can convert to exponential. And so that base of 10 goes here, and then I switch those two. So now x is equal to 10 times 10, which is 100. All right, what about this one? F for fantastic. Log of x is equal to negative 1. So you do this one on your own. There are 2 different ways you could write the answer. 2 different ways. They're not different values. They just look different. So consult with a neighbor when you're done. So how do you write that without the negative? So consult with a friend.
That's not really too cheap.
So what do we end up getting here? Yeah. So again, you got to recognize that your base is 10, right? So the base here is 10, and switch these two. You get 10 to the negative 1 equals x. You cannot leave your answer with a negative exponent. So to take care of negative exponents, we take the reciprocal of the power. The power is 10 to the first over 1. The reciprocal is 1 over 10. Because 10 is raised to the first power, it just remains 1 over 10. Math Excel will accept a decimal. So 1/10 means you have 1 decimal place because there's 1 0. And so that 1 goes in the first decimal place. You have to read to see how they want you to answer. If they say decimals or fractions are acceptable, they always put it in like blue, then you can write either one. If they say only as a fraction, then you have to write them on top. For these ones, I don't care. I personally think the fraction's easier for most of you because some of you don't convert to the decimals correctly. And this would be a non-calculator section of your test, so you wouldn't have your calculator divide it out. All right, so then look at G. Great Gatsby. Log of x is equal to 4, and h log of x is equal to negative 3. So you complete both of those on your own, and let's see what you get. When you're done, consult a friend.
Yeah, get out of here.
That's around there.
We had 1,000 and 1,000.
I got 1,000 and 3 over 10. It's all of those. I got 10,000 and.
Are you just giving up on the answer?
I don't know what I'm doing.
I counted my zeros
I
wrong.
had 4 zeros, so I had 100,000. I'm like, that's
It's okay.
right.
Don't get it. 10,000.
Then I have to double check on my.
I probably did. I got what you got for 10, but I think I had 8 wrong. Did I do 8 wrong?
I got the other one.
That's what I got for you. You got 1 over 1,000.
So that negative seems to bother you all.
Does that make sense? I don't like that.
Okay, so here we go.
Oh.
So G is probably the easiest for you, right? So we identify that the base is 10. So our base here is 10. Switch these, you get 10 to the 4th equals x. And then anytime you're working with powers of 10, if I have it to the 4th, that means I have 4 zeros here. Make sure you put in the commas. Obviously not on Math Excel, but for my test. Then over here, your base is 10. Switch these, you get 10 to the negative 3 equals x. All you have to do is take that negative, and you need to, it says take the reciprocal of the power, which is 10 cubed. Well, that 10 cubed is over 1, so it becomes 1 over 10 cubed. So that 3 doesn't go in the numerator, which is what a lot of you are doing. And then you multiply out the 10 cubed, which means I have 3 zeros here, so it's 1/1,000. And then the decimal equivalency, if it's 1/1,000, that means I have 3 zeros in my denominator. That means I have 3 decimal places here, so the 1 goes at the end of that 3rd decimal place. Are we good with that?
I don't get that at all.
Okay. Let's just say I have 5 to the negative 3. Just take the 10 out of it. This negative right there means I take 1 over 5 cubed. I'm just taking this, which is the original fraction, I'm taking the whole thing and moving it in the opposite direction so I can make the exponent positive.
So why is 10 to the negative
10 to the negative 1 is not
1
different.
different? Like on how we did F.
So 10 to the negative 1 is still over 1, right? If I want that exponent to be positive, technically it's 1 over 10 to the 1st, because I pushed it downstairs so the exponent becomes positive. Well, 10 to the 1st is 10, 1 over 10.
Okay.
So I didn't have to multiply it to anything because it's the first power. So that's the only difference, is you do have an extra step here than we had with the negative 1. Does that make sense? And then here, of course, we'd have to multiply out the 5 3 times. Does that help? Yep? Okay. So let's move on to using our calculator. You'll like that much better. So the calculator one should go fairly quickly. You just need to use the correct button. So let's look at, not that side, this side, example 2. So all we're going to do is, and you notice it says base 10 here?
Yeah.
You're not going to see that very often. Usually it won't be written there. Your log button on your calculator assumes that you're using a base 10, a common log. If you have a base that's not 10, you can't use that button. I'll show you how to get around it. The natural log assumes you have a base of E, which you will always have a base of E for this class. That won't be different for natural logs. All right? So as I do this one, turn your calculator on. I'm just going to hit log, and your calculator is not going to show the base because it's assuming it's a common log for the base of 10. And then 4 divided by 5 and parentheses. Make sure you get in the habit of ending the parentheses. And enter. You're going to round to however many decimal places Math Excel wants you to round to. In my case, we're going to round to 4. So what is this rounded to 4? I've got 0, 9. Does this become a 6, 9, stay a 6, 9, or does it become a 7, 0?
7, 0.
What's next door to the 9? A 1. That is less than 5. So when that's less than 5, we keep this as is. If what is next door to what I'm rounding is 5 or higher, that's when we bump it up there. So it stays a 6, 9. If I were rounding to 3 decimal places, to the 6, what's next door is a 9. So that 6 would bump up to a 7 because the 9 is higher than 5. So this is my round answer, so just make sure you pay attention to what they want. Then you find these, go up to here. So you find those three on your calculator, but make sure when you do natural log that you use the LN button. So find those. I'm going to do them up here as you do yours, and you can check your answers. 4 decimal places. Correct, after the decimals, 4. Yes, that should work. Girls, let's go. No calculator. Why didn't we bring a calculator class?
Because we got
So you might want to talk to Miss Allie over there.
and I wasn't
Watch her do it.
without.
Well, we're just gonna do this real quick. I don't want to have a big movement like this. Because that means, well, I have never had a year in which I have so many kids not having a calculator in their class. So I don't know what's up with it. Log over 9. Natural log of 2 is going to be 0, 26, 9, 3, 1.
Miss Mary,
Yeah,
winter quiz,
next week.
what day?
Don't know. I'll have to look it up.
I think it's Thursday.
And then the last one that I'm having you do, make sure that you know where your E button is. Huh? Oh, you mean this one? Yeah, I know. But it's just as quick when you do X squared. That's why I don't know. But do note that above your natural log, you need to listen. So this is the issue when you don't bring your calculator to class, you're not listening, and then when you go home, you don't know how to use your calculator. So, above the natural log button is an E to the X button. So if you're taking E to anything other than the second power, you can hit that button. But if it's the second power, it's just as easy with the X button. And then for this one, I get 2. Imagine that. Do I really need a calculator for this problem? No. Because what's the base? E. And aren't the bases equal?
Yep.
And when the bases are equal, the answer is the exponent, which in this case is 2. So I really didn't need my calculator, but the point is your calculator will give you that same answer. Alright, so this one's a problem because we don't have a base of 10. So you had this in Algebra 3-4. It's called the change of base formula. It depends on what kind of calculator you have, but you still, even if you have the nice fancier new calculators, color calculators, whatever, you're still going to use my school bus old calculators on your test. You need to know what the change of base formula is. You need to write yourself a note that you're going to have to use that on your test. Most of my calculators require the change of base formula. So the change of base formula for this particular case just means you take the log of whatever the number you're taking the log of, in this case, log of 12, that always goes up top. And the base, the log of the base, goes in the bottom. So we're using the natural log, we're using the common log of the base of 10 to change the base. So a common log of base 10 of 12 divided by a common log of base 10 of 5. So that way I can get around it on my calculator. And all I have to do is log of 12, make sure you're closing those parentheses, divided by the log of 5. In fact, I'm going to clear all of this so you just see these answers. Log of 12 divided by log of 5. And so I get an answer of 1.54 what? 4. So I've got, I'm going to round it to 9, so I've got a 5 here. The 39 bumps up to a 40. So I have 1.5440. Now, if you have a newer calculator, and you'll know if you have a newer calculator, you can go to your math button. So hit your math button, and on the very first menu, you want to scroll down until you see log base. That's the change of base formula that they put into your calculator for you. And if I hit enter, look at what they give me. You just have to input your base, which is 5, and then scroll to the right with your cursor and put in 12 and just hit enter. Did I get the same answer? The calculator had the program in there. But the yellow school bus, or if you have the older brick kind of black calculators, it's not in there in your rinky-dinky, well, not rinky-dinky, he's got a scientific calculator. This one doesn't have it in there either, that would be my guess, but you can still do the same thing on the scientific calculator at home. That calculator that I just showed you, you can use that for everything that you're doing with the exception of the graph. Okay? So that's your change of base. Star it, highlight it. You're going to have to study it because if you're using a newer calculator at home, you're going to go and say, I don't know how to do this on this calculator. And I'll say, well, remember, I told you how to study that. Now, find the natural log of -1, please. What did it say? Yeah. What did it say? That brings us into our next part of the lesson. You cannot take the natural log or the common log of a negative number or of 0. It is not in the domain of logs. So we need to look at the graph of logs. So this is called undefined. And I want you to write here the domain, and I'll show you why in a minute. The domain for log and natural log is 0, not including 0, to positive infinity. So no negatives or 0. The only time that you can input negatives or 0 in for x in a log or natural log expression is if the equation's been transformed and the value is still positive. So, for instance, we're going to look at some problems that reflect that. So can I flip this? Yep. Nope. Good? So let's discuss graphs and why the domain is as it is. So last week, or earlier this week, I guess it was, we explored the exponential graph, y equals a to the x, or y equals a times b to the x, right? That's your exponential graph, where the domain was all real numbers. And we had this horizontal asymptote here of x equals 0, or y equals 0. So that's that one. But then we learned that we can take this and convert it to log form or vice versa. These two are inverses of each other. So the exponential form and the log are inverses to each other. And they were reflected across this line. Y equals x. That's the line of reflection. So they're not reflected over the x-axis or the y-axis. This does meet the horizontal asymptote, or the horizontal asymptote horizontal line test. So because it meets the horizontal line test, it has its own inverse. And the inverse is this graph here. So this is the graph for log of x. The graph for the natural log of x is very, very similar. And so we'll look at those in a minute. But the following things always occur for the graph of y equals the log of x. The domain is always 0 to positive infinity, because when we reflected it over the y equals x line, we now ended up, instead of the horizontal asymptote, we end up with this vertical asymptote of x equals 0. So this vertical asymptote right here changed. So instead, my y is not restricted this time. Remember the y on this one was restricted to 0 to positive infinity? Well, in inverses, don't the x and the y's change? The domain and the range, don't they change? So on this one, if the domain was all real numbers, negative infinity to positive infinity, well, the range becomes all real numbers on the inverse. If the range here was 0 to positive infinity, well, that means the domain over here becomes 0 to positive infinity. So that's why, because they're inverses, those things switch. So we went from a horizontal asymptote to now we have a vertical asymptote. This graph is continuous over all of its x values on the domain. So even though the domain is restricted, it is still continuous along that domain. There are no holes in the function. And you're going to have a couple of questions on your homework that asks you these. It is always increasing because we always go from left to right, determine increasing versus decreasing. So as I go from left to right, the graph is always getting bigger and bigger and rising. The x-intercept is 1, 0. This is a very important point. Because when we translate things, we have to pay attention to the vertical asymptote and the x-intercept. This is affected by up, down, and right, left movements. We'll call them shifts. What is the vertical asymptote affected by? Is the vertical asymptote affected by up, down shifts? Yes or no? No, it's in the same spot, right? Is it affected by right, left movements? Yes. So this is affected by right, left movements only. So right, left shifts. So those are the two things we're going to focus on with transformations. You're also going to have some vertical and horizontal stretches, but those you'll be able to use your calculator to kind of help you with. But on a non-calculator portion of the exam, you ought to be able to move these two things without using your calculator. So before we do that, let's look to see what is the difference between the common log and the natural log graphs. So I'm going to put over here a little graph. I don't know if I mentioned it yesterday, but logs are used to measure sound waves. That's where they were originally created for. So let's look at their graphs. So I'm just going to put the log of x in first, and then I'm going to put below that the natural log of x. So the very first graph that pops up is going to be the log. And there it is. It hugs that x-axis fairly closely, and then the natural log was right above it there. So this one doesn't show that quite as nicely, but this one does. So here, they both have in common this x-intercept though. The natural log and the common log still has all of these things in common. It doesn't matter which one we're looking at. The domain, the range, the vertical asymptote, continuous increases in the x-intercept, they're all the same, whether it's log or natural log. And so they both have this point, 1, 0 in common. So according to the graph we just looked at, and they have the vertical asymptote of x equals 0 in common. So they both hug this asymptote, but the log, this is the log of x, that hugs the x-axis closer than the natural log does. If I asked you what the difference was, that would be what I would expect you to say. Whereas the natural log still hugs this. It still goes to the same point, but it's a little higher. I'm exaggerating a little bit there. It's a little higher than the log. So they both have one point in common, 1, 0. And one stretched a little bit more than the other. That's it. So when we look at transformations, it doesn't matter whether I give you a log or a natural log. Use your expertise that you've developed with transformations to be able to describe them. Even if it's on a calculated portion of the test, you ought to be able to describe what's going on. It's not enough to just be able to plug it into your calculator and recreate it. You have to tell me verbally what the transformations are that are occurring. So this one's fairly simple. What transformation is occurring here? Is it occurring inside the function or outside the function? Inside. Does that affect x or y? Inside the function. It's touching the x, so it's affecting x. So it affects x, is it same sign or opposite sign? Because x is going right, left. Opposite sign. So what's the shift? Horizontal shift, what direction? minus 1, so it would be right 1. So you have to be able to verbalize that. And so here are the things that are affected by that right shift. 2 things I always have to look at before I graph it. Does that vertical asymptote here get affected by the right shift? Yes, it gets moved over 1. So we're going to put we're going to immediately move that asymptote to the right 1. That's usually the first thing I'm going to move. And it's dashed because it is not part of the graph. And you must label it x equals 1. It's going through the x-axis. So it's x equals 1. Then the original x-intercept was here. Logan, you with me here? Who's on? The original x-intercept was here. It also gets moved right 1. So it's going to get moved to the right 1. You must label that point every single time. What's that over there? 2, 0. Those are the 2 big things. Label both of those, and then you just have to sketch in the graph from there. Now, if I was doing this without a calculator, this is what my graph would look like. It's log, so I know it's hugging the x-axis closer than the natural log would. Well, let's look to see what it actually looks like. So if I put in the log of x minus 1. A couple things are occurring. It looks like the graph just stopped here or started there, right? But what's really happening? It's hugging the asymptote, and does my calculator put in the asymptote? No. So because the asymptote and the graph are so close together, it just washes it out. But notice that it is close here. If you drew yours, a little further away, like this one is up here, I'm not marking you off for that. I'm looking, do you know where the x-intercept is, and do you know where the vertical asymptote goes, and do you know kind of how it's hugging it? Obviously, if you're going to hug it backwards and do it this way, that you're going to get marked off. So you don't want to do it backwards. All right, look at this one. Doesn't matter that it's natural log. What's happening? What shift is occurring? Outside. Outside the function. It affects y, so it's up or down, and it's up because it's same sign. So is that vertical or horizontal? Vertical because it's affecting y. So vertical shift up 2. So I've got 1, 2, 3, 4. Does that affect my vertical asymptote with upshift? No. So I still want to label it x equals 0. But my original x-intercept, which is right here, it gets shifted up 2. So 1, 2. Read out that ordered pair and label it. What is it? 1, 2. And then all I have to do is sketch it. I know that I'm going to hug the asymptote. And it's actually probably a little less flat because it's the natural log. So throw that in your calculator. And so it's just with the machine. And we got natural log of x plus 2. And then graph. So I didn't do too badly. Why does it look like it's coming from 0, 0? Yeah, because of that asymptote. I've moved this up, this x-intercept up, and so that means instead of intersecting the x-axis at 1, it's going to intersect it somewhere between 0 and 1, and it brings it closer to that asymptote quicker. And so, again, it's just being washed into that asymptote. Issues with that before we do something a little bit more difficult? Yes? When would I move to the right? On this one? I move them up to this one. This one here? Yes, I move both of those right now. Yeah, I want to pay attention to, is the shift affecting my asymptote? And it always affects the x-intercept. The only thing that doesn't affect the x-intercept is a stretch. Or shrink. Alright, so this one, I actually have two things occurring. So thing one, what's occurring with that? It's inside the function, so it's opposite sign, so it's horizontal, shift, right, 2. Does that affect the vertical asymptote? Right 2, does it affect my vertical asymptote?
Yes.
Yes, it does. So you might want to put a note, affects the vertical asymptote. And then the second shift is this one. What's happening there? Is that horizontal or vertical? So it's vertical, shift, up, 1. So the very first thing I like to do is move that asymptote. So I've got 1, 2, 3, 4, 1, 2, 3, 4. So my asymptote is going right 2, so 1, 2. Put in that dotted line and make sure that you label it. X equals 2. So I'll do the x-axis. You okay with that? That's the x-intercept. Right, our asymptote is always the y-axis. So that's why that one's straight. But you're right, my original x-intercept is right here. So that's my original x-intercept, but it's affected by both of those shifts. So I'm going to go right 2 and up 1. So here's right 2, but up 1. What order of pair is that? 3, 1. And you can always use your table of values if you happen to have your calculator handy on this particular problem, if you allowed it. You could always go to your table of values and plug in 3 and see if you do get 1. That'll kind of help you if you figure out the right translation. And then from there, you just have to hug. It is natural log, so it should be further away from not quite so flat, I guess is my point. Now without a calculator, we've done all of those without a calculator. Anything with vertical, horizontal stretches and shrinks, I will give to you with a calculator. Just let you know. But you'll still have to be able to verbalize what's going on without, I mean, you can look at the graph, but you still have to be able to verbalize what's happening. So this one's a natural log of x minus 2, and then plus 1. So again, you're not seeing that asymptote, and it looks like the graph's got a ghost start, but it actually has gone all the way down there. So know your calculator. Questions on those before I give you something a little bit more technical? Good. Translations make sense. All right, well, they get harder. So let's look, take your paper out that we're working on, the additional paper. And let's do some additional problems for example 4. So let's do A. We've got f of x is equal to -1 plus the log of x. And by the way, if the base of your log changes, I don't think they do that math in Excel. It doesn't affect a whole lot for our purposes here. They could throw that in. I won't do it. So you have to be able to verbalize the translation in words as well as perform the translation itself. This particular translation would not necessitate a calculator. So what is happening? What is this movement is occurring? It's outside the function. It's vertical and it is down. It doesn't matter that I have the -1 in front. Would this be the same as the log of x minus 1? Right? So that can come in the front or it can come behind. So we are having a vertical shift down 1. Does that affect my vertical asymptote? No. So I'm going to automatically label this x equals 0 so I don't forget. And then my original ordered pair was here. So it's getting shifted down 1. So it gets shifted down to here. What is that ordered pair? 1, negative 1. Right, one, left one. And then you just have to hug the asymptote and go through that point. So I'm hugging the asymptote, going through the point this way. I really have no idea where it's crossing the x-axis. And this one actually tends to be really flat because it's the log. Log is flatter than natural log. And look at what it looks like on your calculator. So let's put in negative 1 plus the log of x. So it really doesn't start to cross until somewhere way out here. So it's pretty flat, but it's still approaching this asymptote here. And again, you can go to table of values, second graph, and put in negative 1, or put in positive 1, didn't we come out with negative 1? You can check and see if you actually figured out where that point was. That's not too bad. Let's get another one. This one has several translations. F of x is equal to negative 3 times the log of negative x. Even though you can plug this into your calculator, and this would be a calculator question, and draw the picture of the graph, most of the points are going to come from you having to describe what's going on. So let's start off with just the negative in front of the 3, because the 3 is separate from that negative. Negatives always mean what? What's the word? Not flip, but reflect. So it's a reflection. Is this occurring outside the function or inside the function? Outside. It's outside, right? So if it's outside, it's affecting the whole function. The whole function is y. So that means it's affecting y. So where does it get reflected? Y. Over the other one, the x. So reflections are always opposite. So think if I'm reflecting, I'm going in the opposite direction. So think opposite of what it's affecting. So it's a reflection over the x-axis. What is this negative doing? It's inside the function. Still a reflection. But because it's inside the function, it's affecting x. Anything inside affects x. So if it affects x, we will be over the y-axis. So I'm purposely color coding these because we're going to reflect them separately. So let's just stop there for a moment and let's just perform those reflections. The reflections themselves do not affect the asymptote. So originally, my line was here. And this is a log. So that's your normal log. Y equals log of x. So I dotted it on purpose because that's not the graph I want. So the reflection over the x-axis, if I reflect this over the x-axis, this point here is on the x-axis. So it doesn't reflect. So instead, let's you look at the tail end of your graph here. This tail end is this far from the x-axis. So I want to go that far here and plot a point. This tail is this far from the x-axis. So I want to go that distance over here. But I still want to go through that point. So that means I'm now hugging this asymptote and going through this point. And you see now that that's a reflection. So that is y equals negative log of x. Then from the red one, we're going to reflect it over the y-axis, so do the same thing. But what's nice is this point is not on the y-axis, so that point gets reflected the same distance away. So it's reflected 1 unit away, over here. And then reflect the tail. So the tail is over here. I'm going to reflect it the opposite direction over the y-axis, same distance. And then this tail is over here. I'm going to reflect it the same distance. So right there. Kind of helps you get to what you're supposed to be hugging. And so then this is the second translation of y equals negative log of negative x. So that has both translations in it. That's your double reflections. We have not accounted for, however, the 3. What does that 3 when it's being multiplied do? Is it a stretch or a shrink? Is it being multiplied to the outside of the function or the inside of the function? Outside. And 3 is a number greater than 1. So what do you propose it is? A stretch. So if it's a stretch, won't I be stretching these tails going vertically this way because it's outside? So what's going to happen to this? It's going to get closer to the y-axis, theoretically. Let's see if that's actually what happens. Nobody should have their head on a desk. Because what that means is that what Mrs. Murray is saying is not important. And that's clearly not true. All right, so negative 3 log of negative x. There's that double reflection. And let me just put in here for chuckle's sake, just the plain log of negative log of negative x. Just without the stretch. Didn't it get closer to the y-axis? It got pulled out. So then you're going to, I don't know why you're packing up before I'm ready to be packed up. So then you're actually going to go through that same point, and it gets pulled closer to both sides of that y-axis. And so this is your final answer right there. Now I wouldn't expect you to get that stretch on your own. There's one more that we'll do tomorrow, but this is the reflection that we'll look at tomorrow. So I'm just going to throw that up there for chuckle's sake. So remember, if you have 3 minus x, change it to negative x plus 3 so that you see OSA left translation, a left shift, and a reflection over the y-axis. By the way, when you move to the right, that axis of reflection changes. So I ended up reflecting over the x equals 3 instead of the x equals 0. And you have a couple problems like this.
Yeah.